Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about a specific application of Le Chatelier's principle, namely the common ion effect. So the common ion effect essentially deals with a system that's already in equilibrium, except for now we're adding in a second substance that contains an ion in common with that equilibrium. So let's again assume we're dealing with our good old friend acetic acid. It can decompose to form acetate and hydronium, and again with a given equilibrium constant. So as soon as I put acetic acid in solution, I should quickly achieve equilibrium. However, if I'm going to end up adding, say, acetate, I'm never going to end up adding it just as acetate because no ion occurs on its own. In practice, I'm going to end up adding some sort of salt that contains one of these two types of ions. So either something that contains acetate, like sodium acetate, but I can also add in a common ion that contains a free proton, like HCl. By adding in a common ion that affects either one of these two species, I can essentially drive the reaction. And we looked at this a little bit last time. In general, though, the most important type of common ion effect that we're going to see with acid-base behavior is the addition of either a conjugate base or to a weak acid solution, or a conjugate acid to a weak base solution. So if I'm going to add a conjugate base to this system, what we're going to see is this reaction will shift towards reactants. And the reason why this will be very important is because it will affect the amount of protons in solution. Because as I move the reaction towards the left, I'm going to consume any free protons that are present. And as a result, as the amount of free protons goes down, the pH will essentially increase. And this makes sense as I add in a weak base. And then we can go ahead and try and determine the exact pH using an ice table. So let's go ahead and try and look at the pH of a solution that's 0.1 molar in acetic acid, but 0.05 molar in sodium acetate. So the first thing we're going to note is the sodium really is going to be a spectator ion here. And so what I've done is I've really added a solution of 0.05 molar acetate. So if I go ahead and set up the ice table, nothing looks too surprising yet, except for the problem here is that I don't just have 0.1 molar of my weak acid, I also have 0.05 molar of my weak base. Then as the reaction proceeds, since I have no free protons, if we checked our Q, it will be 0, so we're going to move towards products. So we're going to end up generating more acetate and free protons and consuming a little bit of the acetic acid. However, when we go ahead and plug it in here, you'll notice that we aren't going to generate that many protons. Small Ka, 10 to the negative fifth, that we can probably ignore the X in these combined terms. So as I set up my Ka, again, products over reactants, I put in that 0.05 plus X times X over the 0.1 minus X. So this plus X and minus X are really going to be very small. So let's go ahead and drop those terms. So now suddenly the term is 0.05X over 0.1. Well, this ends up simplifying down to 1/2 X. Okay, that's actually fairly interesting. This isn't a sort of dynamic we've seen before, but it's fairly common when we're looking at acid-base reactions. So now if I want to go ahead and solve for my hydronium concentration, this is going to be the same as X. So this means that X is going to be the same as twice my my dissociation constant. So I'm going to have a hydronium concentration of about 4 times 10 to the negative fifth. We can then go ahead and turn this into pH by doing the negative log. And suddenly we have a system with a pH of about 4.45. So this system is actually going to be fairly acidic. But if we compare that to what would happen if I added a 0.1 molar acetic acid solution with no acetate, that would be much more acidic. And this is a very natural sort of phenomenon we see. And if I end up adding a base, the system will be more basic. And specifically, we're going to find that the pH is going to be a lot more stable at these sort of intermediate conditions. And we'll go ahead and focus on that a little bit next time as we apply a little bit more mathematical rigor towards this sort of problem. However, we can also look at how the common ion effect impacts percent ionization. So let's go ahead and take something like hydrofluoric acid, another weak acid. So it will decompose to form fluoride and free protons. This is actually a fairly good way to try and introduce fluoride into solution. Now, what would end up happening if I let the system go to equilibrium and I add sodium fluoride? So first of all, we will end up increasing the concentration of fluoride. But it turns out that much less of my original hydrogen fluoride will essentially break apart. So the reaction will shift to the left and it will decrease the degree of ionization. I won't essentially break apart that much of my hydrofluoric acid. Most of it will indeed stay together. However, what would happen if I added sodium chloride? Just switch that fluoride for chloride. Well, it turns out it's not going to have any sort of role. Sodium won't affect the pH, and neither will chlorine. And neither of these form an ion pair. So when we're looking at the common ion effect, we're looking for things that will affect the concentration of one of the ions, typically on the product side. If whatever solution we're adding doesn't affect one of those ions, it won't have any impact on the reaction. So this is an important thing to keep in mind on when we're looking at increasingly complex acid-base systems, which can contain multiple weak acids or bases. We're only really going to care if it affects the pH or a conjugate acid, conjugate base or acid. So next time we're going to look at a little bit more mathematical rigor at these weak acid, weak base pairs. Until then, take care.